Hello, everyone. My name is Wenqi. I'm a PhD student in the Department of Engineering and Cybernetics in Norwegian University of Science and Technology. Today, I would like to share our work as the optimal management of the peak power penalty for smart grids using MPC-based reinforcement learning. With electrification of our society, the home-scale controllable energy system is increasingly deployed. This kind of system usually have energy consumption parts, production parts, and storage part. However, there's one significant issue in this kind of smart grid system. All the houses connected to a local transformer. And this local transformer must be sized according to the peak power encountered in the system, which will incur high investment costs for the distribution system if the peak power is very high. So this power distribution companies trying to reduce the peak power consumers impose on the system. There are some economic incentives. And the ideal way is to collectively invoice the consumers behind a given transformer for their monthly peak power. However, solving this problem is challenging because of the stochastic nature of the local power production and consumption, and because we want to minimize the monthly cost. So it's a fairly long-term problem. If we use traditional way like MPC, it's not that easy to solve. Nowadays, people try to use some RL-based strategies because RL can use real data to reduce the impact from disturbance or stochastics. And also it can solve the long-term problem. And traditional RL use NN as a functional approximator. In our work, we use MPC-based RL approach. So why we use MPC-based RL approach is that for NN-based RL, it requires huge amount of data to learn from scratch. And it like a form of tools to satisfy constraints and to evaluate stability. And last, there's no physically meaningful way to choose the N hyperparameters. However, for our MPC-based RL approach, it can use the known information, for example, the system's dynamics, and the system constraints can be easily handled. Last, because of the theoretical support behind MPC, it enables us to do some theoretical analysis. Moreover, thanks to RL, system uncertainties can be overcome to some extent, and which can solve long-term problem. And last, this MPC-based RL approach is a performance-driven approach rather than model-driven approach. It means that here we focus on the performance. We want to improve the performance. The figure shown here is a typical three-agent residential smart grid model. And the SOC here is the state of charge of the battery, and delta is the power production consumption. I equals to 1 to NA means we have NA agents. And B here is the binding, the amount of binding power from grid, and S here is the selling amount of selling power to the grid. And the local power production consumption is assumed as a random work model here with some stochastic delta. So you see delta based on Gaussian distribution with some mean and covariance. We also have some system constraints on the state SOC, which should be within 0 and 1, and the constraints on the inputs binding selling amount should be less than some maximum amount. From the RL perspective, the state S should be the SOC and the delta for all the agents, and the control input A is the binding selling amount for all agents. So the objective function for this problem is that we want to find a policy pi to minimize this closed loop cost that sums from 0 to the end of the month, capital K. This cost function has two parts. First part is the spot market cost. The other part is the peak power cost. Let's first look at the spot market cost. It is a summation for all agents of their spot market stage cost, which is defined by the difference between buying and selling profit. It's a buying and selling difference you get. And the peak power cost is some coefficient times the peak power during this 1 month period. To get this PPK plus 1, we need to define a variable p peak k, which is defined by this one. It means that for p peak k plus 1, it is a maximum value between the previous p peak and the current maximum between the summation of binding and summation of starting from each agent. And p peak 0 is defined as 0. So in this settings, the p peak power in the whole time interval should be the p peak k plus 1, right? That's why the peak power penalty should be times some coefficient. However, for solving the RL problem, we should have a stage cost rather than this kind of form. That's why we define a peak power stage cost LP as this way. And you can prove that by having this one, finally we can have this similar equation here. So now our RL stage cost is defined as two parts: the spot market stage cost and the peak power stage cost. And this is our standard RL formulation. So we want to find the policy pi to reduce this J, which consists of both spot market cost and peak cost. Now let's talk about our MPC-based reinforcement learning approach. The idea here is that we use the MPC as a function approximation. So consider the following MPC scheme parameterized by theta. This one is the MPC cost with some parameterized stage cost and the terminal cost, and the parameterized peak penalty cost. These two lines and system dynamics, instead of using a stochastic model, we use some theta here, which is a deterministic model. And these two are system constraints for state and inputs. And this is the peak power variation equations. And the last line is MPC initialization. So you can see for the parameterized function, we have this parameterized stage cost function, terminal cost function. And for the parameters, we have these parameters, including alpha, delta, theta lambda, etc. And by the way, the parameterization is arbitrary and you can use other options. The question here is that why we need these parameters. This is because there's mismatch between the MPC and RL formulation. The MPC horizon could be fairly small. Here in our case is 12. However, for the RL, the problem horizon should be 1 month, right? So it's fairly long. And the cost function is different for this too. And also the system model is different. In RL, we consider stochastic model, but in MPC, we consider deterministic model. So you'll see that because of these mismatches, it's reasonable that we parameterize the MPC cost functions, models, constraints, etc. And then RL adjust these parameters theta according to the principle improving the performance function J. And theoretically, under some assumptions, if the parameterization is rich enough, the MPC scheme could capture the optimal policy in presence of model uncertainties and disturbances outside the stochastics. And this theory has been mathematically proved in this paper, and if you are interested, you can take a look. And the rich here means that higher dimensional theta means more thetas and more universal parameterization functions. And finally, the obtained deterministic policy we get is the solution of the MPC. You see it's the B0 star and S0 star. And for the total system, it should be the policy for each agent. Now the question is that how should we update this theta? We use the LSTD-based deterministic policy gradient method, DPG method. And this is a standard equation. And the gradient with J respect to theta is calculated by this equation, where the first part is derived by doing some sensitivity analysis, where R is the KKT conditions and L is the Lagrange function. And the second part is calculated by this equation, where this Q omega is a compatible Q approximator, and VV here is a V approximator, where W and V is calculated by using the least square method. And finally, we can get this aptitude for theta. And this is a parameters values we use for the simulation. And this is a machine we use, and the runtime is about 8 hours. and average runtime per MPC is 4.3 seconds, which is fairly enough for the practical application. Here is the results. You see that this is the variation of the parameter zetas over learning steps. And you see all the parameters converge as learning progresses. And here we show the parameter zeta lambda, because this is a fairly important parameters in our MPC scheme. You see that with learning steps, the zeta lambda is increasing, means that we have more consent on the peak power cost. So the peak power should decrease to reduce the peak power cost. And you see that the peak power really decreases from 42 to 11. And this figure shows the gradient of performance function with respect to parameters, and it finally is getting there in this converge. And our monthly cost is getting decreased with learning. So in this work, we try to do solve an optimal management for the peak power cost for multi-agent smart grid system. This kind of problem is stochastic and is long-term problem that makes the problem challenging to solve. In our work, we use a parameterized MPC scheme as the optimum policy approximator, and we use the LSTD-based DPG method to update the parameters. Finally, we get a fairly good policy that can minimize the monthly spot market cost and peak power cost. For future works, we will focus on the scalability of the proposed method. We want to deploy a distributed MPC scheme that the control can scale up easily to larger multi-agent system. That's why we need to investigate the possibility of the distributed MPC RL approach. That's all. Thank you.